So today I will talk about Rutherford scattering formula. Rutherford scattering formula. So let me first of all talk about that. What is Rutherford scattering formula? And this is a very important experiment. Rutherford scattering. Is a very important experiment, and this leads to the idea of or the nuclear model of atom. It gives us the idea of nuclear model of atom, and this experiment is performed in 1911 by Lord Rutherford. It's performed, and what he did, he has taken a parallel beam of alpha particles. So what is alpha particle? Alpha particle is basically 2He4, or in other words I can say that the helium nuclei. He has taken it and bombarded alpha particles on what? On the gold foil. On a gold foil, and the gold foil is very thin. So what he expected, say if it is a gold foil and it is bombarded with the alpha particles, then before Rutherford's model it is assumed that positive and negative charges are equally distributed in the atom. But if it is equally distributed, and say if it is bombarded with the alpha particle, then what will happen? If so many alpha particles are, so then there is a equal distribution of this scattered radiation, so it can be scattered in the different directions. Equal distribution will be there. But actually what is observed, let us have a look at that. This here I am taking a I am using this website to show this that what actually will happen. This is the animation. Rutherford scattering experiment. It is in the O labs, and you can see this animation here. So for example, say let me start it, so and let me show the levels. Just a minute. Just see, say alpha particles are coming from here, they're coming in this way, and they're bombarded on this gold foil. And if we try to look at the pattern, say most of the particles are crossing this gold foil and very few particles are coming back. And this basically, this is a zinc sulfide screen. So that means what? That means very few particles are coming. So that means inside the atom there is a lot of empty space. So that means if it is a, this is what? This is a say atom, and so only say a very interesting fact will be observed that say alpha particles is coming in this way. Only out of 10,000 number of particles which are bombarded on the gold foil, roughly one atom, one alpha particles retraces its path. Say 10,000 particles are hitting on this, and out of this 10,000 are scattered in this direction, and out of that only one particle is coming back. So that means there is a there is a roughly 10,000 times smaller positive charge is concentrated at certain point, and that point is known as the nucleus of the atom, right? So that means a idea of the nucleus will come out, emerged out of this experiment. Let us have a look at its zoomed view. Let me stop it. Yeah, this, and let me go to the zoomed view of this one. See, let me clear the screen. Yeah, now let us have a look at it. The very interesting experiment. Yeah, just have a look at it. See. So let us start this. This is a zoomed view of this particular experiment. Say alpha particles are coming. Mostly alpha particles are crossing, but very few particles they are coming back. Just see, this is one particle. See, very few particles are coming back. That's what is happening. Because now in the new model that the positive charge is supposed to be concentrated here. Say, these particles are crossing, but this one particle which is, so that means a whole of the positive charge is concentrated at a very small region, and that small region is known as the nucleus. Now in this lecture I am not going to talk about a complete detail of this, but here in this lecture I will tell you that this is a mathematical formulation of the Rutherford scattering formula, that how that scattering formula will be derived. So let us derive it mathematically. So suppose there is a nuclei. I am not considering here gold, but simply a positive nuclei will be here, and say plus Ze is the charge on it, say, and it is the axis along which particles are coming. Say this is the axis along which the particles are coming. Say alpha particles are coming in this way, and Coulombic potential will be there. Say alpha particles are coming in this way. So what will happen when a alpha particle is try to reach here? Then what will happen? This particle will go like this, and say its impact parameter will be v, small b, and say let us consider another particle whose impact parameter b plus db. Say this distance is b plus db, or in other words I can call this as db. So if the particle is coming this way and it is a little bit away from here, then what will happen? This particle will follow this path. And let me redraw this backward. Just a minute, yeah. So if I redraw it, just a minute, yeah, and it will go like this. So that means it will go this way and this will go this way. So here this angle, say this angle is theta, and say this angle is d theta. So that means if impact parameter will be larger, say for this impact parameter b, scattering angle is theta, and for impact parameter b plus db, the scattering angle gets decreased, so it is said to be theta minus d theta, as this is clear from this particular diagram. So this will form a annular ring. Say will form a annular ring, and what is the area of this annular ring? Its area of this annular ring is said to be a annular ring, its circumference multiplied by its thickness. Area is said to be its circumference into its thickness. So what is its circumference? So if its radius will be db, so it is 2 pi b, its circumference is multiplied with its db. So that's why it's said to be 2 pi b db. It is the area of this annular ring. And now let I be the intensity of incident beam, and it's a beam of alpha particles. So if I will be its intensity, and intensity means number of particles coming from unit area in unit time. So therefore number of particles per unit time crossing annular ring, and whose area will be this. So that means this number is say dn, it is said to be area multiplied by intensity. Area multiplied by intensity, it gives that number us. But let me now recall the definition of what we call the definition of that is basically the definition of differential cross section. If I recall the definition of differential cross section, then from that we can also estimate the number of particles scattered per unit time into solid angle d omega, and this angle, solid angle d omega, is represented by 2 pi sine theta d theta by a single target, as we have as I've talked about it in the earlier lecture. And this is represented by again dn, and it is nothing but it is the I sigma theta, means differential cross section is the d omega. It is represented by like this. So it is minus I sigma theta, and its value as I have shown here. So it is 2 pi sine theta d theta. And what is this negative sign? This negative sign basically it shows that as theta decreases, as b increases, right? As is clear from above, where because when b for the corresponding to scattering angle will be this, and when b will become b plus db, then scattering angle will become theta minus d theta. So negative sign basically indicates that signature here. So but these two quantities will represent the same number of particles, both talk about the same thing. So that means from this equation 1 and 2 I can equate these two things. So therefore one can write down as the 2 pi b dbi is equal to minus I sigma theta 2 pi sine theta d theta, and this 2 pi will cancel out with this 2 pi, and this I will cancel out with I. So from here I can write down sigma theta is equal to minus b sine theta db over d theta. Now there is a standard relationship between there is a standard. I will talk about that in other lecture. So there is a standard relation between impact parameter and scattering angle, that is B is equal to ZE square over 4 pi epsilon naught E and cot of theta upon 2. This is a standard relation. I will derive this later on, but you can, for the time being, you can remember this relationship between scattering angle and the impact parameter. So using this, I can calculate, say V is equal to this one. So if I use this relationship, then I can calculate the dB over d theta, and dB over d theta is basically the derivative of this one. So it is ZE square 4 pi epsilon naught E minus cosecant square theta by 2 into 1 by 2. This is the derivative of cot theta by 2. So what should I do? It will become minus ZE square 8 pi epsilon naught E cosecant square theta by 2. So let me put these two values here. So if I substitute these values here, then what I am getting, this is, let me do it here. So let me decrease the size of this, then I can, so say is equal to, say what is the value of this ZE square? So minus, so the value of this will be minus ZE square 4 pi epsilon naught E cot theta by 2. This is its value, and divided by sine theta, then minus ZE square over 8 pi epsilon naught E, it is cosecant square theta by 2. This minus into minus will become plus, so I can write down it as a Z square, and let us put these two together. So it is Z square E raised to power 4 over 4 pi epsilon naught E. This is sine theta upon 1, so I can write down as a 1 over sine theta, and this is cot theta by 2. Cot theta by 2 means it can be written as cos of theta by 2 over sine of theta by 2, and there is basically, so I can write down it as a 1 over 2 into 4 pi epsilon naught E and cosecant square theta by 2, and here this can be written as sine theta by 2 sine theta by 2 cos of theta by 2. I just put 1 over sine theta here, so it is Z square E raised to power 4 over, this is 4 pi epsilon naught is sitting here, 4 pi epsilon naught is also sitting here, and so it is 4 pi epsilon naught whole square. This E and this E, it will become E square, so it is cos of theta by 2 sine of theta by 2, and say 1 by 2 is also sitting here, this 1 by 2, and it is cosecant square theta by 2. So this cos theta by 2 will cancel out with it. So this 2 and this 2, it will become 4. So I can write down it as a z square e raised to power 4 over, and sine theta by 2, sine theta by 2, when they goes up, they will become cosecant theta by 2. So it's two terms, so it will become cosecant square theta by 2, and one cosecant square theta by 2 is sitting here. So that's why I can write down it as a 4 into 4 pi epsilon naught whole square e square cosecant square theta by 2. So this is the required Rutherford's formula. This is required Rutherford's scattering formula. Rutherford's scattering formula. This is a very simple formula. You have to basically first of all say remember this thing, and another very interesting thing that you have to remember is that let me go back. This is a important thing said, that you have to relate these two things, right? When we relate these two things, correlate, then we can immediately derive this very simple formula. And I will try to in the next lecture try to show you that how this thing will comes out. So that's all for this lecture.